Hi guys, my name is Connor with UConn HKN, and today we're going to be solving an AC circuit problem and finding the node voltage at a point Vx. This circuit has capacitors and inductors, so it may seem a little bit complicated, but we can just treat these as resistors. We're going to be using rectangular and polar coordinates to deal with these, and we'll be using two AC voltages, which we can convert straight to polar. And we can do that by this you can think of as the R, and this you can think of as the phase angle. So V1 is equal to 1 angle negative 45 degrees. And V2 is equal to 2 angle 45 degrees. These are the phasor voltages in the circuit, V1 and V2. So we solve out this problem the same as we would a simple problem with three or four resistors. So the first thing that we see is we have a parallel resistor and capacitor, so we can combine those with R equal the equivalent resistance equal to 1 over first resistance. They're impedances. They're technically impedances, but we can treat them as resistances. Plus 1 over the second resistance. And this ends up equaling, if you type this into your calculator, this will equal 0.3 minus 0.9 J. And it's actually good practice to keep your J's in front, just so you can see them first. I make the mistake a lot, but I like to just keep them in front. Next, I'm just going to redraw the circuit to make it easier to see. It'll just be a V1 with a block for resistance. Usually we will denote impedances in block form and just write the complex rectangular form of the impedance like that. We can write them all in block form just to be consistent. And here we have 5 ohm resistor from above and a 2J ohm. So in order to solve this out, we'll do a simple KCL and write down the 3 currents in the circuit: I1, I2, and I3. So the currents going in equal the currents going out. So I1, so I1 plus I2 is going to be equal to I3. And we can denote I1 as the V equals IR, voltage over resistance. So V1 minus Vx over R. Plus I2, which is the current's going this way, start at this side, V2 minus Vx over 5. And the final voltage, Vx, we should denote this as ground. So with the ground being 0, Vx minus 0 all over 2J. So now we have an equation, and we see our only variables right now are V1, V2, and Vx. We're trying to solve for Vx, and we're given V1 and V2. So we can just rearrange this equation and solve for Vx, and we'll have our answer. The only tricky part is dealing with all these J's and phasors, and you might mess up with the math there, but just double check your answers whenever you're doing these, and it should be straightforward. But just doing the algebra out, we end up with v1 over 0.3 minus j times 0.9 minus vx over 0.3 minus j times 0.9 plus v2 over 5 minus vx over 5 is equal to vx over 2j. Start writing up here. Move all our vx's to one side. We end up with v1 over 0.3 minus j 0.9 plus v2 over 5 is equal to vx over 2j and plus vx over 5 plus vx over 0.3 minus j 0.9. And here we can just combine these and pull out a vx and have vx times 1 over 2j plus 1 over 5 plus 1 over 0.3 minus j 0.9. And here's where you can just type this straight into your calculator and make sure you're in A plus BI mode. And this will come out to Vx times 0.533 plus 0.5. Well, I'll keep the j's in front. I'll be consistent. Plus j times 0.5. And on this other side, we will plug in for V1 and V2. And right now we have an phasor voltages, so I'll write them as such and have 1, negative 45, all over 0.3 minus j 0.9 plus 2 angle 45 all over 5. So here you have to have them in the same form in order to work with them. So at this point you could work with either form, but usually when you multiply or divide complex numbers, it's better to have them in polar form. So I'm going to convert these two into polar form using these equations. And so r will equal a squared plus b squared, where this is a and this is b. You can see that. And the same here, where we don't have a j term, so the b will just be 0. So this will give us 1 angle negative 45 over r is 0.949. Our angle phi is given by the tan inverse of the imaginary over the real. And that's just b over a. And when we type that in, we get negative 71 degrees. And same thing over here. That will be over 5 angle 0. So at this point, adding or multiplying and dividing polar is easy because the r's will just divide like normal fractions. So this term ends up being 1 divided by 0.949. And the angles add or subtract depending on if you're multiplying or dividing. So if you're dividing, the angles will subtract. If you're multiplying, the angles will add. So this is angle negative 116.56. And This one is 2 over 5. And we subtract the angles, 45 minus 0. It's 45. And that's equal to the same Vx. And I'm just going to divide both sides by this 0.533 plus j times 0.5, which we found here. So divide this by that. And same thing, you could convert these to rectangular or convert this one to polar. Just to go back to rectangular, I'm going to convert these back into rectangular. And we can do that using these two. So the A term is just r times the cosine of this angle, and the B term is r times the sine of that angle. So we'll end up getting negative 0.471, actually minus, not a plus, a minus j 0.943 plus 0.2828 plus j 0.2828. And that was just converting these and these using those two equations. And then we end up in the bottom, just what we had before. And at this point, you can just type this right into your calculator. And as long as you're in that A plus BI mode, you'll end up with the right answer. So then, once you type that in, Vx is equal to negative 0.806 minus 0.48. Put the j in front again, because I mess that up all the time. Minus j times 0.483. And we can convert this back to polar using the same equations. It's equal to 0.939 with a phase shift of 30.93 degrees. And we actually convert this back into time domain using the same logic. This Vx, the r is just the magnitude, and the angle is just whatever we would plug in right there. So Vx is equal to 0.939 cosine of, we pick, these omegas are usually the same. I think in this problem, I didn't write it down, they were actually equal. My bad, you can't see that. But omega 1 was equal to omega 2. So we can just use the same omega here. And that would be a plus 30.93 degrees. And that's the answer for Vx, solving from an AC power. Thank you very much.